Okay, so here we are visiting our shader again. At this point, we've got it set up so that basically we have written our own Phong shader that has a texture on it. Now what we'd like to do is spend just a few minutes and talk a little bit about bump mapping.
Yep.
Now there's a few different techniques for doing bump mapping.
There's the traditional approach.
The traditional approach, which uses grayscale maps to simulate areas that are pushed in or pulled out.
Right, and basically at that point, all you could do was bevel geometry up or down.
Right.
There wasn't any push geometry to the right or left or anything like that.
Exactly, and that's where normal mapping comes in. Normal mapping's the big thing over the last, year and a half or so. And so what we're going to do in this video is show you how we can use a normal map to make our object appear as if it has a lot more detail on it, detail that's not there.
Yeah.
And then we're going to go as far as in the next video, show you how to get this information into our own custom application so that we can say, hey, we have a bump mapped object.
Right.
Okay, so doing this, before we start really messing with anything, the heart of it lies back in that equation,
right.
The formula. As a matter of fact, do we still have that up, Joel? If we pull this up, if you think about it, basically what are we figuring out here? We're figuring out the color of what each pixel is going to be in the end. And lighting plays a very big role in it. The ambient plays a big role in it. All these things play a big role in it.
Right. Basically, the final value of each pixel is dependent on this equation right here, n dot L.
And n is our normal.
Right.
So if we were to doink with the normal, we would obviously be changing the intensity of the light at that particular pixel.
Right.
Which
in
could
effect
simulate some sort of self-shadowing or make it look as if something was pushed out because it's a bit brighter, etc. And that's exactly what we're going to do here. Up to this point, Joel, if we go ahead and switch back over real quick to RenderMonkey, and let's go in and take a look at how we're handling the normal now. So right now we're just saying in the fragment shader, we're just saying the normal in normal is equal normalize the normal.
Right.
That's it.
The normal was set when we took the normal directly from OpenGL and multiplied that by the normal matrix.
Exactly. So now if we were to go in there and start changing that, let's go back over to the fragment program. As opposed to just normalizing our normal now on that vec3 in normal line, if we were to go in there and put something else.
Yep, like referencing a texture, perhaps.
Yeah, so instead of using the normal that's coming in from our geometry, we use the normal from a texture. Now, how is this texture generated? Well, let's first go ahead and change our textures. Let's change to a texture that has a normal map.
All right, let me add a texture, and let me add fieldstone bump dot.
Okay.
And if we take a little bigger view of this, what you see here is a normal map that has not just black and white information, but actual color information. So the RG and B channels represent X, Y, and Z for that normal.
So how do we get this? Well, that's really up to you guys. Nowadays, a lot of the more recent 3D applications are now supporting the ability to take high-res geometry and bake out a normal map for you. And this just means that you're going to go in there, take a piece of geometry, and just detail it to death while you're modeling. I mean, the Unreal 3 characters have been advertised to have, 2 to 3 million polygons.
Right.
And, of course, we're not going to have 2 to 3 million polygons running around in real time times 10 if we had 10 characters.
Yeah.
That's going to just get crazy.
Very much so.
What they do is they have their modeler create this very high-res model, and then they use a plug-in or internal elements that are built into the application to then take that high-res geometry and bake out a normal map, and the normal map is going to contain basically what the normals are doing all over that geometry, but now in texture form. Then we can take a low-res piece of geometry, and we can use this map, we can sample off of it to give the low-res geometry our own normals on a pixel-by-pixel basis. That's the key thing here. So even though our low-res geometry is low-res, since we're going pixel-by-pixel, we have the ability to simulate tons of detail as if, by mimicking self-shadowing and illuminated areas, etc. So that's what we're going to do here. So let's go ahead and change the texture that we have, the cloud texture, over to a texture that matches up with that one.
So fieldstone, so let me just look at this real quick.
Okay, so here's just your regular, your regular one, texture, and now we have, of course, our normal map.
Right, this guy right here.
All right, so we're going to use these two guys together.
So let's add this into our path. So we add a texture object, and let's reference the bump map here. And we'll just leave this at cloud texture just for now. And we'll call this guy bump map.
Okay.
And let's just go out and change this to, I don't know, ground texture, maybe?
Yeah, that's fine.
Or ground map. And now these reference the correct things.
Okay.
Now if we come back over into our fragment program here. Let me just copy and paste this sampler line. So let's get our ground map. And let's not forget to get our bump map as well. And let me quickly change where I utilized cloud texture before. Right. So ground map, I think that's the only place I used it.
Yeah, you isolated it quite nicely.
All right, so now we're getting that information. Let me go into the vertex program. There's a few things that we're going to need first, and that is the binormal and tangent. So let me just add these in here real quick, and then I'll explain this in a little bit more detail. So rm underscore binormal and attribute vec3 rm tangent.
Yeah.
And basically what this is, of course, you have a normal, and you have a tangent to that surface, right? The binormal is simply the cross product, as we talked about before, of the tangent and the binormal. Excuse me, let me roll back a second. We have the normal, and we have the tangent that's going along that surface.
Right.
The cross product of those two is going to give us the binormal. So the binormal, tangent, and normal are all perpendicular to each other.
Okay.
And we can utilize these to... well, basically start knowing in which direction everything goes, because it's basically our coordinate axes.
Right. As Joel holds up his hand now, giving you the index finger, you do the little...
right hand rule type
thing. That's right.
All right, so how do we start utilizing this? Well, let's go ahead and do some calculations here, just some temporary variables. So we have our vec3, and let's do our n normal. And this is going to equal our GL normal matrix, which we're doing down here. Multiplied by GL normal, and we need to get our binormal and tangent as well. So let me just copy this 3 times. So n binormal and n tangent. And again, attribute. This is something that's going to be passed into us from OpenGL because it's an attribute. And this is going to be our normal matrix multiplied by rm underscore binormal and rm underscore tangent. And in a second, I'll explain where we get these values from.
Okay.
Light direction, we'll just leave that like so. View direction, actually, light direction and view direction I'm going to have to slightly modify here. And just a second, let me just kind of take this out, move this to the bottom here. All right, so we have our light direction that we're moving around. But in this case, we're going to have to slightly modify this. Let me go ahead and block this out again. Sorry about that. So we have vec3. Let's make these local variables. So vec3 n view direction. And now my final view direction and light direction, I'm going to make them equal to something a little bit different. We're going to take the dot product of the tangent with the n view direction. All right, n view direction was what we were using before. It was our vector v. And now we have our view direction, and we're taking the dot product of that and our tangent. So our v, we're taking v dot t. And what this is allowing us to do is find out how much t is going in the direction of v, right?
Okay, right.
And we're going to store that into the x component of our view direction. So it's simply a different way of doing it and finding how much the view direction is along the tangent.
Okay.
So let me copy that. And we'll do y and z. And the same idea here, except this one's going to be the binormal. And the final one's going to be the normal. And then finally, we're going to do pretty much the same thing for our light direction. We're going to take the dot product of the tangent and tangent with the light direction. And copy this 3 times. We have our y, our z. This is going to be our binormal and our normal. And, of course, this is going to be light direction. So at this point, we have our view direction and we have our light direction as vectors with respect to our tangent, binormal, and normal vectors.
Right.
And with that, we can come over to our fragment program and implement our bump map so that we can actually start utilizing this guy. So right here with our normalize, we're going to change this around a little bit. Instead of just using the normal, we're going to change this completely around and say texture 2D bump map. So we're now sampling from our bump map and passing our text chord. And then we're going to get the XYZ of this and multiply this by 2.0. And let's see, following my parentheses here, and minus 1.0.
Perfect.
So we're now getting the normal from our bump map and storing that into here. So if I compile this, and come over into my shader effect, look at that. It looks kind of sort of right, but look, when I come onto this side, it looks like kind of like an X-ray shader.
Oh, wow, yeah. Pretty freaky.
Yeah, something's not right here. And the reason for this is because we're not getting the correct... Remember, we created our... If we go back into our vertex program, we have our RM and our binormal and our tangent. And again, this was something that we created that we're utilizing right here, and it needs to be correct because we're basing our view direction on these normals,
right?
On these vectors, if you will. So we know our normal. This is being passed to us every time with our GL normal call. But these guys, they're not, and they need to be correct. And what you can do is switch our stream mapping. And by default, this is sending us the position, normal, and texture coordinate. As we've used these many, many times, we need to add more to this so that we can start using our binormal and tangent, and this will automatically generate it for us. So if I add this in, I'm going to add my binormal and add in my tangent as well. So this is going to automatically generate it for me. However, both of these are going to need to be a float 3. So we have our normal. This is being sent to our program. Now all we're doing is adding binormal and tangent so it can send both of these to our shader as well.
Okay.
So let me go ahead and press OK on that. Press F8. And check that out.
Wow.
It's now black. It should be correct. Let me go ahead and move my light around. Instead of multiplying by the model view matrix, I'll simply have the light move around. So let me copy and paste this guy. And simply take the light position and minus the object position. So compile that. Come over to here and check it out.
There we go.
There we have a nice little bump map effect.
Very nice. Can you go ahead and change that over to like perhaps a cube model or something?
Oh, sure. Come into model, change the model over to cube.
Yeah. Very big difference. That's why I wanted people to see that.
Yeah.
And remember, we want to bring this over into our own application.
Yep.
So in order to do that, that's why I want you to have this as a cube. That looks so nice. The specularity on that's amazing.
Yeah, it's very nice.
And I think you've put the code in place to do that. Wow. So, yeah, in the next video, what we're going to do is take a look at what's required to bring this over into our application so that in the application we have at least seen one object that has a form of bump mapping on it. We'll talk about that, and we'll also use the new shader class to make it very easy. So with that, unless you have anything else to add, that wraps it up for this video here. Thanks a lot, everyone.